Hello everyone. So my name is Michael Grederson, and I run a company based in London called GraphAware. And what we do for a living is travel around the world and make sure that people succeed with Neo4j. And today I would like to speak about one of our recent projects, something that's very much based on our experience, and that's our recommendations engine library. So I'm going to be speaking about recommendations in general in the first part of the talk, and explaining why graphs are very well suited for recommendation engines. And I would like to go over some business and technical challenges that are sort of connected to building a recommendation engine. And finally, I will also dive into small amounts of Java code, introducing the GraphAware recommendation engine library. So, since you've joined this webinar, you probably all know what recommendation engines are and what they could be used for. So here's just a couple of examples why people would want to build a recommendation engine. So it could be for stuff you're selling to your users, or recommending other users to your users. So for example, dating sites or social networking sites. It could also be twisted around, and you could start recommending who the buyers of a product that you're trying to sell should be. So there's a number of applications for recommendation engines. And if we look at the literature around recommendation engines and blog posts and things that are published, there's typically two kinds of recommendation engines people are talking about. The first kind is so-called content-based recommendations, which are based around features of the items that we're trying to recommend. So it could be the genre of a movie, or the category in which an item is being sold, and so on. The other type people talk about are collaborative filtering engines, which operate with the notion of relationships between users and items. So your users will have some kind of relationship with the items. So for example, in an e-commerce store, it would be that they looked at it, or they liked it, or they rated it, or they bought it. And then based on those relationships, we will try to recommend these items to other users. The good news is that these features, as well as the relationships between users and items, can be quite naturally represented as graphs. So just to give a very simple example, here we have a simple graph with two users on the right, and two movies in the middle, and some genres in the left. And we'll see both categories here. So the feature part, so the feature recommendation engine, we could build by looking and representing in the graph what genres are assigned to those movies. So that's the left part of the graph. Equally, we've got relationships between users and movies. In this case, the two users have rated the movies, and they've all rated them with 5 stars, so they very much like them. There's also a third kind of the inferred one, the interested one down at the bottom, where we can see that because somebody rated a movie quite highly of a genre romance, then it might indicate that the person is interested in the genre itself. So that's an example how you model both kinds of recommendation engines as a graph. Graphs are very good for these engines for a number of reasons. The first one is they're very easy to understand. So I've just shown you a graph, and you could instantly see, and if I go back to it, you could instantly see what that means. So that means users rated movies, there are some genres, and so on. So you can read it without any prior knowledge of anything. The other reason why graphs are a good fit for recommendation engines is that many domains are very natural. Graphs are a very natural way of modeling these domains. So in this case, we just draw it on the whiteboard, and using circles and arrows, that's what the graph looks like at the end. The third reason is that Neo4j, a lot of graph databases, and Neo4j especially, are schema-free, which means that you have a very flexible way of representing all kinds of things, and you can evolve your model over time. So if you start capturing other information on top of what you've already captured in the graph, it will not break your existing structure, your existing data, and your existing code, because you basically just start adding different kinds of relationships and different kinds of nodes into your graph. Finally, graphs are very fast to query for recommendations and for many other domains. Neo4j has its own query language called Cypher, which I think many of you have seen before. And Cypher is great for a quick proof of concept when you want to test things and build like a very simple recommendation engine. It's also very great for smaller data sets. I'm talking about, let's say, hundreds of thousands or maybe millions of nodes. And also very good for relatively simple logic. So if I show just a simple example, let's say we wanted to recommend some movies to people again. And the way Cypher works is that we would express patterns in the graph, and we would express those patterns on the whiteboard and then transform it to ASCII art effectively. And so in this case, what you see the query, if you just look at it for a while, I think it will be very easy to understand what we're trying to do here. So we're trying to find a pattern, and that's the first few lines, where a user liked a movie, and the same movie was liked by another user. And we're trying to find on the third line of the query another movie, which is our potential recommendation that the user liked, that another user liked. And then in the second block of the query, we're trying to make sure that the potential recommendation that we have found has not been seen previously by the user we're recommending to. And that's it. Then we return the recommendation, and we'll effectively get a set of recommendations for the user. So that's a very simple way of creating a Cypher query to recommend something to users. However, requirements of a real-world recommendation engine, as you can imagine, are much more complex quite often. So let's look at the reality. Imagine for a moment that you're building the people you may know feature on LinkedIn. So I'm sure everyone on the webinar is using LinkedIn, and you know that LinkedIn suggests people you may know. So when I'm delivering this presentation live, I'm asking people to come up with a few ideas about how you would go about building that engine. How would you know that somebody might know somebody else? So think for yourself for a moment how you would go about doing that. And since I cannot hear you, I'll probably have to skip to the next slide and give you the answer, or some of the answers that we have found building some recommendation engines for this kind of domain. So you could, for example, say that on your site they have some contacts in common, and therefore they have a good chance of knowing each other. You could also, because people, when they sign up with Facebook, they give you the appropriate permissions, you actually have portions of the Facebook graph represented in your own Neo4j graph. So you could see that they have Facebook friends in common. You could also, if they install your application, there are APIs where you could see their mobile contacts. And so you could see who their mobile contacts are and whether they have signed up to your service and suggest those people. You could also talk about or find people that have worked for the same company during the same period of time, or studied at the same university or school. They might share the same interest, live in the same city, and so on and so forth. So there's a number of ways we could go about suggesting people you may know. But now if we think about it, it is actually even more complicated than that. So if we go back and revisit those ways of finding people you may know, we will realize that, first of all, if you have more contacts in common, is there a better chance that you know the person in question? And how much better is that chance? If they lived in the same city, or study in the same school, or work for the same company, does the size of the company matter? And the answer is probably yes, because if you, let's say, worked for IBM, the fact that somebody else worked for IBM doesn't necessarily mean that you know them very well. But in case the company is very small, let's say under 10 people, then the chances are pretty high. We're talking about people's emails in address books and common emails and contacts, but there's many email addresses you realize that don't represent a real person. So these could be support emails or some info@acompany.com. These need to be probably filtered out, and same with phone numbers. And then we need to take care about recommending only the relevant things. So we want to filter out people that have already connected on our site, so we don't recommend somebody who already is your contact. And people that have a pending invitation, for example, and people that have indicated they have no interest in connecting with the person in question. And if we have shown a recommendation many times, and the user we're showing it to hasn't reacted to it, then that probably means something as well. So there's a number of business challenges that we have identified building these sort of real-world recommendation engines. And the first one is finding things to recommend. So finding things in the graph that are potentially a good item or person to recommend. The other challenge is serving the most relevant recommendation. So once we have found things to recommend, we need to sort of make sure that, excuse me, that we sort it and serve the most relevant ones. Also, a lot of people and organizations embarking on some kind of a recommendation engine project will have some idea of how to recommend and what to recommend, but will not be sure. So they'll be building a proof of concept, and then with that comes the responsibility of you actually measuring the quality of recommendations that you're serving to your users, so that you can adjust your recommendation engines to serve more relevant recommendations. Finally, you want to understand before embarking on such a project what the time to market or cost of development or ROI will be, or have some kind of indication. In terms of technical challenges, there are a few as well when we're building a recommendation engine. So the first one is clearly performance. So the reason people are using these new technologies for building recommendation engines is one of them is performance, because we do want to serve recommendations in real time. And the reason is that the only worse thing than no recommendation is actually an out-of-date recommendation. So if you have ever seen Jim Weber speak about Neo4j, he uses a great example where in a supermarket, when you have just bought a PlayStation, you get a voucher for 20% off of an Xbox. That is actually a harmful recommendation. So we, as much as we can, we want our recommendations to be based on most up-to-date information that we have. Secondly, because typically when embarking on a project like this, we will be changing it, and we will have many people on our team. Simplicity is quite important for other people, developers and non-developers, to understand how the recommendation engine works and what's being done and what can be and needs to be changed. Finally, when we know what we're going to change and when we're going to update the engine or make it more clever or make it serve more relevant recommendations, we need to be flexible enough so we can do that easily without too much development cost. So we've built 4 different recommendation engines, production-ready ones, that in the past, let's say, half a year. And what we've learned, we've tried to distill into an open source recommendation engine skeleton that will help you solve the challenges. So I will speak a little bit about that and introduce the open source project. So this recommendation engine project that's on GitHub is a plugin to Neo4j. So it's an open source part of the GraphAware framework, which is all open source on GitHub. You can Google it. There's quite a lot of blog posts and documentation around it. And you have to use a JVM language, so Java or Scala, because it's built for high performance and it's built using Java. And it has an opinionated architecture that you kind of have to follow, which we think is good for building these recommendation engines. But it is opinionated, but in return it gives you fast results and a very flexible way of building a recommendation engine. The library handles all the plumbing, so what you focus on is just implementing that business logic that only you know. So we've made a few design decisions building this library, and I'm going to briefly go over those. The first one is that there is one what we call engine per recommendation reason. What that means is when I presented that list of different ways of recommending people you may know, each one of those ways would be a separate recommendation engine plugged in. So you could easily build the whole solution as a puzzle or pieces or Lego pieces, just assemble it together. Each engine executes a graph traversal and finds items that are potentially recommendations. And these engines can be assembled into higher level engines, like building blocks, to keep some flexibility and encapsulation. So back to our graph that we presented earlier, you could easily see, for example, if I wanted to recommend something for Bob on top right, I could go about it by saying, well, so he's seen American Pie. If that's what genre comedy, what other comedies do we have? Love Actually, that's one of them. So that would be a sort of genre-based recommendation. We could also say that Bob has rated American Pie quite highly. There's another person that rated that movie highly, and that's Alice. And Alice has also highly rated Love Actually. So there's another way we could discover the same recommendation. So these would be two different engines discovering the same movie. The next design decision is that we think that items that are discovered multiple times are more relevant. And I've just demonstrated one way an item could be discovered multiple times because it was independently discovered by different engines, but it could equally be discovered multiple times by the same engine. So a typical example is this people in common, people you know in common. You will land, if you imagine a graph traversal, you will land on the same potential recommendation multiple times if you have multiple connections in common. And we think the relevance depends on how the item was discovered as well. So the way you discover could bear a different relevance in the total recommendation. Right. Finally, we think that items that are not to be recommended, which must not be forgotten, are a cross-cutting concern. In other words, we don't want to pollute the logic of the engines that discover items to recommend by putting this if-else or some checks at the end of every one of them to filter out items that we do not want to recommend. So the items we don't want to recommend might be, on a dating site, people of the with too much of an age difference or the wrong gender, or in products we don't want to recommend items that are out of stock, and especially not items that the user has already bought. So we think these should be encapsulated somewhere else, but definitely not in the engines themselves. So the architecture that we came up with is the following. We have an input, which is the person or user you're recommending to. And that's an input to an engine or set of engines. And the output is the recommendations for the user. So that's quite simple. We have a concept of scores and score transformers. So the whole library assigns scores to those recommendations and keeps them sorted by descending relevance. And you can transform these scores into different ones, and I will show you why you would want to do that. And for those transformations, you would use transformers. Third, we have blacklists, a concept of blacklists, which are items you know upfront you don't want to recommend to a user. For example, people he already knows, or item he has already bought. You know that as soon as you have the input, you know what the blacklist should be. And you can compute them upfront before discovering the items that you would recommend. Related to that are filters, so they're similar. They are to exclude items you don't want to recommend, but they're after you have found a potential recommendation. So filters could be for things that you need to know the recommendation discovered before you're excluding it. So if you find an item, then you can look, is it out of stock? Yes, then I exclude it. So these kinds of filters would be to filter out recommendations after they have been found. We have a concept of post-processors that can adjust scores based on additional criteria. So for example, if you were looking to recommend people you may know, the fact that a potential candidate for recommendation lives in the same location as the person we're recommending to could mean that we should increase the score a little bit. And equally, we could penalize results. So in a dating site, if we wanted to recommend people you should date, we could penalize age difference, for example, by implementing a post-processor. There's a concept of a context, which spans the whole computing process and knows a number of things about the whole process. So for example, how many recommendations do we actually want to produce? How fast should we produce them? How much time we have? How much time has elapsed? And so on. Finally, for recording the recommendations that we've produced, and especially information about those recommendations, such as why they were produced, how long did they take to produce, for analytic purposes, and for basically being able to find out how relevant the recommendations are, we have a concept of loggers. So you could implement loggers into the skeleton that store flat table-like information about the recommendations that have been produced in something like Cassandra or relational database or a flat file. So to put this into practice, let's try and build something by looking at a few lines of quite simple Java code. So what we're going to try to do now is, in 5 minutes, we're going to try to build a simple engine that recommends who you should be friends with. And we're going to follow a sequence of steps that are related to the architecture that I have just presented. So step 0, sort of a preliminary stage, is to come up with a graph model. So we're recommending people you should be friends with. So the model we're going to be working with here is just a very simple model with 2 kinds of nodes. We have the purple ones, which are people, and we have the green ones, which are cities. So people could be friends with each other, and people could live in cities. And each person, as you can see in the top, in the bottom right corner, they just have a name and age. So let's see how we could work with this model to recommend people you should be friends with. So first step is to discover all potential recommendations. So not caring about whether you're already friends with these people or whether it's yourself even who we're trying to recommend. Let's just find people that are potential candidates. So the way you would go about that in our engine library would be to just extend a class that's provided called something in common, and only provide the relevant information that only you know. The type of relationship, the direction of the relationship. So in our case, it's bidirectional because we're talking Facebook-like friendships where it's mutual, and the name of the score that's going to be produced, in this case, friends in common. So with just a very few simple lines of Java code, we have just built the first part of our recommendation engine that will discover all the potential recommendations for people you should be friends with. Secondly, if I go back to the engine, it will for each potential recommendation discovered, it will give it 1 point. I know we want to do something with the score, maybe, because if you think about it, the difference between 1 and 2 people in common, or friends in common, is probably much higher in terms of relevance for the recommendation than the difference between 10 and 11 people in common. So in this case, we're going to be applying a Pareto function to say the more people you have in common, the smaller the differences between the scores, the increase in the scores. So we're just going to add one more method here to our friends in common engine, the one on top, that's a score transformer, where we're going to say, please use this Pareto function to transform the scores. The maximum score we're going to produce is 100, and the 80% level, that is 80 points, you'll get when you have 10 friends in common. So even if you had 1 billion friends in common, you will still have 100. Third, post-processing. So once we have found all these different people that we could recommend, we could, for example, reward the fact that they live in the same location. And again, this would just be done very simply by extending a class called reward something shared. And again, you only provide the information that only you know. So we're talking about outgoing lives in relationships. And if these relationships from the person you're recommending to and the person you're trying to recommend point to the same location, we give 10 points, extra 10 points to the whole score of the recommendation. There's another one which doesn't extend the class, it simply implements a post-processor from scratch. We're trying to reward same labels or same gender in this case, so they're both male or both female. So you don't have to look into detail here into this method, but it's just the very last line there. It's adding 10 points for the node we're recommending and the node we're recommending to, in case they have the same gender. Number 4 is we want to filter out irrelevant recommendations. And again, there's some pre-built building blocks for you to do that. So one typical one would be, so we're going to be implementing a context factory now, which is the component produces the context, but the context factory knows about the blacklists and the filters I was speaking about. So let's look at the top part here, the blacklists first. We have a existing relationship blacklist builder, which basically says, before you embark on this whole recommendation journey, build a list of people that the person is already friends with, so we don't have to recommend them, or we should not recommend them. And of course, you can build your own blacklist builders. And for filters, there's one that is quite self-explanatory. It's called exclude self, which means don't recommend the person who's being recommended to. Yep. By the way, the exclude self isn't both, because it could be used both as a blacklist builder and a filter. So that's our third step, filtering out irrelevant recommendations. Finally, or almost finally, we can assemble these pieces together to build a full-blown, ready-to-be-used recommendation engine. So extending Neo4j top-level delegation engine, what we call, you can just plug in the pieces we just built. So we're looking at the engines, there's friends in common, and then we could plug in another one called random people if we don't have enough. We plug in the post processors, the rewarding same labels, rewarding same location, we're penalizing age difference, and all kinds of things. And so by looking at this, you could just show this to someone who just logged onto this webinar, and they would probably be able to understand just by looking at this what we have built. We have built a friends recommendation engine, and it works by finding friends in common, and by putting in some random people and rewarding things and penalizing things. So it's really easy to understand, and at the same time, it's very, very flexible, because as you're building new engines and new components and new filters, you're just plugging them in. This class you're looking at is a full-blown recommendation engine. You can use it now, and I'll show you how. Before I do that, this optional step of pre-computing. So our framework has the capability of pre-computing recommendations using the very same engine you've just built. And the reason you might want to pre-compute them is sometimes some algorithms will be simply too expensive to compute in real time. And we have a capability in the framework to detect when the database is busy and when it isn't busy. So when the database is less busy at night during quiet periods, we'll ramp up the background computations and pre-compute recommendations using the same logic that you've just developed. And so we'll build relationships between people and their potential recommendations, and we can serve them immediately by just reading them from the database rather than computing them in real time. Of course, applying all the filters and stuff. So this is, again, our friends computing engine that we have seen a minute ago. And this is a new top-level engine where our friends computing engine is the very, very last line. So it's, again, plugged into it. And in front of that, we put a Neo4j pre-computed engine that's also a pre-built component. And we're serving potentially pre-computed recommendations before going into real-time computation. So the capability is there as well. And as you see, you can just, again, just put pieces together. Number 6 is the logging I was talking about. And again, very simply, into your recommendation engine on the very bottom of the screen now, you just say what loggers you want to use. And they will record recommendations and record statistics about them to wherever. So in this case, this is just an implementation that logs it using SLF4j to a file or to a console. But you could implement a Cassandra logger or anything, or message queue logger, and so on. And this is, again, to be able to record recommendations and why we serve them, so along with their scores. So once a person accepts it by either buying an item or connecting with the person in question, we can measure how successful our engine is and how relevant the recommendations we're serving are. Finally, we want to do some testing, of course. So I'll demonstrate how we would use this engine. So in the very first line here, we are calling that engine we've just built and saying recommend me 2 people, which is the last parameter, for a person named Adam from our domain. And do it in real time, please. And what we get back is 2 people, as we asked, and then we also get, if we want, the scores, so the reasons why this recommendation has been served. So for the case of Vince, for example, you can see that the total score is 19 point something. They were penalized for age difference, and they had 14.8 for friends in common, and they rewarded 10 points for same gender, and so on. This is the output you would see once you've assembled the engine together. This is just another way of testing it, so you could inspect the recommendation object and assert that the scores are what you expect them to be, and the people that are recommended are the ones that you expect. So hopefully we have solved most of or all of the business challenges. So we started finding things that we should recommend. We also introduced the concept of scores and scores transformers, and the fact that these are handled by the framework to serve the most relevant recommendations. We have a way of measuring the quality of the recommendation. So each recommendation that's produced has a UUID, a unique identifier, that you can store along with the scores, why it was produced. So if at some later stage, a user accepts or rejects the recommendation, you can match it against the scores with which it was produced. And hopefully we have sort of shown that it's not that hard to build a recommendation engine, so the time to market or cost of development is kept reasonably low and reasonably predictable. For technical challenges, most of the stuff we've shown is real time, and this is running in production at a number of our clients. The largest one is about 100 million nodes in the graph, and it's serving recommendations below 100 milliseconds each, as in a set of recommendations below 100 milliseconds. And hopefully you've seen from just looking at the code that it's pretty simple and flexible. So you can understand it by looking at it, and you can replace components and add new ones and so on. So if you wanted to get started with this, it's very simple. You declare the recommendation engine library, which is in Maven Central, as a Maven dependency in your project, and you're good to go. There's documentation on GitHub, so you probably want to have a read through that. And of course, there's more stuff. So I haven't talked too much about the ability to pre-compute recommendations, but that's very much implemented already. There are other built-in base classes that you can use, and of course, we welcome additions. So if you find something missing, this is an early stage project, so there will be things that you will need and you need to build yourself. We will be glad if you contribute. That's the address for GitHub. I think it should be fairly easy to Google. For the future, we're planning to build some algorithms or more algorithms out-of-the-box algorithms to serve recommendations, all kinds of clever algorithms as well, such as clustering algorithms and maybe a bit of machine learning as well. We're planning to implement a time-based participation policy. What that means is we're planning to, very soon actually, to be able to say, I want the best recommendation you can produce in 100 milliseconds. And so whether an engine and a component participates in the process or not would be determined how long it has taken so far to compute the recommendations we have. We are planning to look at computation engines integration. So, for example, for the clustering, exporting parts of the graph into, let's say, GraphX or Apache Flink, and then writing the results back, is something we're looking at quite actively. Machine learning, I've mentioned. The algorithms and the scoring weights, could be self-learning, which would be really good. And this whole thing is part of the GraphAware framework, which contains many more modules, and generally the purpose of that is to help you build generic and domain-specific functionality on top of Neo4j. So if you're interested in exploring that further, there's also a few other modules that are quite interesting for many users of Neo4j. Modules that track changes in the graph, like the change feed, modules for representing time in Neo4j called the time tree. There's a PageRank module. There's a library called GraphUnit, which I encourage everyone who's developing with Neo4j to check out, because that makes it really easy for you to test your code that talks to Neo without introducing any dependency. So it's just a test dependency. And there's a few more. Everything's open source, pretty much active, production ready, so it's in production in a number of clients. It's on GitHub and it's in Maven Central. We try to release a version compatible with the latest release of Neo4j within a few days. So now the latest one is 2.16. I mean, Neo4j 2.17 was released just a day ago or 2 days ago, so we're probably going to release a new version of the framework tomorrow. So that's active. So I encourage everyone to try the code and the libraries and give us some feedback if you can contribute. And of course, build your own modules. That's what it's built for. And we are in the consultancy business, so if you need any support or consultancy, we are available. Here's a calendar of events. Some of them we've already done. So we have spoken about this at FOSDEM, which was a great event. Today, right after this webinar, if anybody is dialing in from London, we have a meetup in our office where we're going to try to get people hands-on. So they're going to build their own recommendation engines within an hour or two using this library. If you happen to be up north, we are doing a training on the 10th of February in Manchester. This is an introductory training to Neo4j. So it's a one-day training, and in the evening there's a free meetup in Manchester where we're going to speak about something, probably recommendations again, or maybe some other things. And there's a training in Edinburgh that we're running on the 17th of February. There's also Graph Connect, which is a very important event for all Graphy people. On the 7th of May in London, 6th is the trainings, 7th is the main conference day. This is organized by Neo Technology. We'll be there, and many other interesting people will be there. So if you can make it, please come over for the 7th of May to London. I thank you very much for your attention, and then we have quite some time for questions. So if anyone has any, please type them into the chat. Thank you very much.